Hello random viewer and welcome to a video on climb performance. Yes, I know, probably not the most exciting topic, but any airplane that you're flying, we are going to have to get from our starting altitude up to our ending altitude, or our cruising altitude, whatever that might be. So how do we actually calculate how we're going to get from that starting altitude to that ending altitude? Well, that's the topic I want to cover today. Before we get into that, a quick disclaimer: my experience is limited to light fixed-wing airplanes and instructing out of those. If you are not flying a light fixed-wing airplane, these methods may not apply. A fighter jet, for example, has the performance to climb nearly vertical. That's going to negate many of the methods that I'm teaching today. At the same time, several concepts will hold true, but if you're flying a fighter jet, this probably isn't the video for you. If you are working on your private pilot or another rating though, I hope this is a resource that you can come back to and try to get some help whenever you run into one of those tough problems of, well, how much fuel is it going to take me to climb, or how much distance am I going to cover? Hopefully this video can be for you, so watch it as many times as you need to. If you haven't noticed, I do have a habit to ramble and go on to side tangents about this or that. Hey, did you notice that I'm building an airplane? You know, crazy stuff like that. I'm going to do the best I can to divide it up into segments to stay on track as much as possible, but be aware that there are several concepts that do have a habit of popping up here, there, and everywhere. So if this is your first time watching and you do want to know a lot about calculating climb performance, please do watch the whole thing, do your best to follow along, and the next few times go back to just the sections that you need. This video is not for someone who is just an introductory knowledge of aviation. This is pretty in-depth. I'm going to be using a lot of technical terms that you may or may not know. I will also link some videos in the description that you should probably watch before you watch this one, such as one by Free Pilot Training on how to calculate takeoff performance for a Cessna. Also, another thing you need to be aware of: you as pilot in command are responsible for planning out the amount of fuel, time, and distance it's going to take you for any flight. I am not a replacement for that. These methods are to help you, but please know that this is not a replacement for real flight instruction. I am a flight instructor, but I am not instructing you specifically. This is a generalized video to be a reference that is helpful. I am not trying to get in the way of your instructor, nor replace your instructor. Please do get some actual flight instruction and knowledge in these areas. With that out of the way, let's get into it. In preparation for this video, I put out a post asking for some suggestions of flights that we could use just to demonstrate the process of planning. I only got 2 replies, which is fine, I guess, and they both had this common theme of starting from somewhere near Charlotte, North Carolina. So we'll go with this Salisbury. Yuzochi only wanted farthest possible. There's a lot of different ways that could be interpreted. I'm not going to go there today. Bozeman, Montana, that's pretty far. So there is a common thread there. And that's where we planned this out. This is problematic. Covering a flight this long is way beyond the scope of a video on calculating climb performance, but we'll have to tuck that away for another day. For now, we will just stick with this as our general direction of flight, and we'll zoom in here on SkyVector to Salisbury, Mid-Carolina. We'll take off and we have a course of 311 or 311 degrees. Before planning out the climb though, we need to know what altitude we're climbing to. So that involves some looking along the route and seeing what we can find. So when we first take off, some of the highest obstacles top out just over. Here's one that's up at 2,500 feet. Obviously we don't want to be too close to these. Here's a congested area, Statesville. Legally we'll need to be at least 1,000 feet above the top of the highest obstacle there. So there's 1,203 feet. And there's another one at 1,220, something like that. And then add 1,000, so that would be 2,220 feet. These are all pretty low altitudes and probably not where we want to be cruising this time of year. Well, as of recording this, it's August. It's hot and bumpy, and I don't like being down low because, well, it's miserable. Now, as we continue surveying our route, the terrain becomes a problem. Now we have mountains that are coming up to 3,000 feet. Oh, I don't want to do that. Okay, so don't grab the route line and mess with it. Anyways, we'll continue looking along here. Here we have a 4,600 foot obstacle. Keep going, there's 4,600 feet again. All kinds of things around this 4,600 feet or so. Oh, and there's one that's almost 6,000 feet above sea level. So we want to be quite a ways above those. And another thing to be careful of in the mountains are these wilderness areas. FAA wants us to be 2,000 feet above the ground in all of those. So 6,000 feet would be a good altitude to aim for. So now that we have an idea of roughly 6,000 feet as a minimum for terrain clearance, the mountains get lower after this. The highest part of the Blue Ridge Mountain Range is right in this area. So once we clear that, I know that we're good for quite a while until we have to stop for fuel, because we will definitely have to stop for fuel on a trip this long. Now let's go over to aviationweather.gov. We're going to need quite a few pieces of weather information. And the first one I'm going to want is going to be under the forecasts, winds, and temperatures aloft. And we can see quite a few here. We want one that's near Salisbury, which is roughly in this area. We could use Raleigh. We could use Tri-City. Since we're going to be flying over the mountains and heading northwest, let's go ahead and use this TRI, Tri-City. We could do that here, messing with these things. I'd rather not. I like more precise, so we'll go here. Tri-City appears to be in this sector here. Let's see if we can find it. There it is, Tri-City. So this is the winds and temperatures aloft. And we can set the time however we like. So we could go later in the day. This is 4 o'clock in the morning to 11 o'clock in the morning. It's currently 9, so I'm probably not going to be leaving in the next 2 hours. Let's go ahead and go up to the next time. There is no wind or temperature reported for 3,000 feet here, probably because of terrain or just how close to the ground 3,000 feet is for Tri-City. Now, the next place we have a wind forecast is at 6,000 feet, and it's 9900. There's no such thing as 99 degrees, so this means the wind is calm. 9,000 feet, still wind's calm, and it will be 12 degrees Celsius. That's pretty nice. Now, 12,000 feet, now we have a little bit of wind. This is 310 at 9 knots. Here's how this works. 310, so you just add a 0 to the end of the first two numbers, and that's our wind direction. So it's coming from 310 degrees. If you look at our route, we're doing 311 degrees. So that is as direct a headwind as you can get. And it's going to be at 9 knots, so those next two numbers. There we go, 9 knots. We have 7 degrees Celsius. That is ideal. I do like having a nice low temperature. We could be at 9,000 feet where we have calm wind, so we're not fighting anything, or 12,000 feet where we are fighting. Because we're likely flying under visual flight rules and heading west, we need to be at a even 1,000 plus 500. So that would be 12,500 feet. If you remember from your regulations, 12,500 feet is the altitude where we start needing supplemental oxygen. So 12,500 to 14,000 feet, we can spend 30 minutes there, and then we need to start using supplemental oxygen. Problem is, the planes that most of us have access to, myself included, do not have supplemental oxygen, so we can't really be cruising up there at 12,500. So 10,500 feet would be about the highest we can do. That said, different people react to altitude differently. Just because I do fine at 12,000 feet does not mean that you or someone else is going to do fine at 12,000 feet. Even though we're below the legal minimum for oxygen, most people are starting to suffer mild hypoxia around 8,000 feet. So your mental performance will be down a few percentage points. That's a problem when we're operating an aircraft. Just something to be aware of. If you've never flown that high, go with an instructor or someone who is comfortable flying that high, and just get an idea of how it affects you. Also know that you will feel fine. You'll actually feel really good. That's a sign that you are hypoxic. So the better you feel, the more concerned you should be. Hypoxia is something to consider in a different lesson. Talk to your instructor about it. So we could pick 8,500, maybe 10,500. These are some good altitudes. At 10,500 feet, we're about halfway between this 9 and 12. So we would expect our wind to be halfway between 0 and 310 at 9. Because there's no direction here, we can assume this 310 degrees, and half of 9 knots would be 4.5. So what I just did there was interpolation. So say we picked 10,500 feet for our cruising altitude, we need a wind that's halfway between these for our planning purposes. Say we were dealing with a different altitude. Here we have 310 and 280. Well, halfway between those, if we were halfway between these two altitudes, would be 295 degrees. And then our wind is 14 versus 9, so halfway between those would be roughly 11.5. So that's how interpolation works. Now notice, there I just went halfway between. If we were cruising up at 14,000 feet, that's not halfway between 12,000 and 18,000. That's closer to 12,000. So we pick somewhere that's between these two, but closer to this one. And that's how you make an educated guess, or what a lot of people call interpolation. So a reasonable estimate for the wind at 14,000 feet, just by looking at these two numbers, would be somewhere like 300 degrees at maybe 10 or 11 knots. Keep that trick in mind for later. We're going to use this interpolation thing a lot. Anyways, not dealing with wind is a fantastic idea, so we will go ahead and go with, let's say, 8,500 feet. That gives us plenty of clearance from obstacles. It gives us our even 1,000 plus 500. Hypoxia is a minor concern rather than a moderate concern, getting up to 12,000 feet. And temperature is going to be pretty decent. Now, winds aloft is not the full story. We also need to look at the winds at the surface at Salisbury when we're taking off. Once we make it up to 6,000 feet, we can expect those calm winds. But up until then, we might have some other issues. So we'll go back to the homepage on this website. METARs would tell us what the winds are doing now. So if I were to type in down here, our Salisbury Airport, here we go. We get our METAR, or Routine Meteorological Report. It's the 5th day of the month. Yep, that matches. 13:05 Zulu, so that's 1305 minutes past the hour. Converting that to local time, I just know that this time of year in this area, subtract 4. So that's 9:05 in the morning, 26 minutes ago. Not bad. It was an automatic observation. Wind was 320 at 3 knots. 10 miles, visibility, sky clear, temperature 23, dew point 21. So right now the sky is clear, but because the temperature and dew point are less than or equal to 2 degrees apart, we could expect some fog or low clouds as a possibility, something we just need to be looking out for. Altimeter 3002, that's pretty nice, a little above standard. That means our engine will perform a little bit better. AO2, so it can tell us what kind of precipitation there is. If there were any, there is not, so I'm not too worried about it. So that's what the wind is doing now. This is great for picking which runway to use. So if I were to look at this Salisbury Airport, we can see which runways they have. Click on that. Pull up the airport diagram. They have 2 and 20 on the runways. Wind is 320. Well, that's a pretty nice crosswind there. But we'll probably go with runway 2. So, things to think about. If we were taking off now, we would be using that runway 2. But we do need to look at what the wind is going to be doing later in the day, since that's the time we're taking off. We used our winds and temperature aloft for 15 Zulu and later, so that's at least 11 o'clock. Let's just call it 12 o'clock for taking off. So we're going to need to know what the weather is doing at that time. Knowing what the wind is doing now is great and all, but we do need more than that. So that's where the TAFs come in, the Terminal Aerodrome Forecasts. And as before, we can type it in. That's not good. Looks like Salisbury does not have a TAF. And if you can't find an airport that issues a TAF, we can use this map and find one nearby. There's Greensboro, and there's Charlotte and Hickory. Well, we don't want to use Hickory. That's getting too far into the mountains. Charlotte is an option. Greensboro is an option. Let's see, which one's the closer, Greensboro or Charlotte? Yeah, Charlotte's just a hair closer. There we go. Now we have a TAF. We were looking for 12 o'clock local time, or what is that? 1600 Zulu. Oh, there we go. 5th day of the month at 1600 Zulu. That will work nicely. Wind is 050 at 4 knots. Definitely using runway 2 at Salisbury. That's going to be the most into the wind. And 4 knots, pretty light. But this is good. This is what we needed. So we're really lucky today. We don't have too much wind to factor in. We could assume that there is no wind in our climb performance and get a very accurate estimate because there is very little wind. It's negligible. Now, on windier days, that will absolutely affect our climb performance. But that's going to complicate matters. For now, we're going to go ahead and do an example without wind. Actually, a few examples without wind. And then later at the end, if you want to learn how to factor in wind, we'll do that. So here are the notes that I took while I was doing that weather portion. We have our route, we have our winds aloft for the Tri-Cities Airport, we have our selected altitude, what we decided just based on the winds and temperatures. We have our terminal aerodrome forecast, so that's going to be our expected winds at takeoff, still pretty calm. And then in the time that we looked at it and I switched out here, we had a new METAR come out for Salisbury. So it was, I'm trying to remember, 1305 Zulu. Now they came out with a new one, 1345 Zulu. So 45 minutes more up to date, I guess, or 40 minutes more up to date. I can do math, probably. I'm about to do a video on how to do math. Whoops. Wind is now calm, 0, lots of zeros. Still 10 miles visibility, sky still clear. New temperature and dew point, so fog is not too much of an issue anymore. And altimeter 3002. That has not changed. This is all very important information, and we'll get to why. But first, let's fill in our navigation log. So I'll bring this over. You would put in the tail number for the aircraft that you're using. I'm not going to put that in for this because we're going to be trying to plan this out for a few different kinds of aircraft, so I can show you how to do the calculation different ways. So your first checkpoint in your navigation log is our departure airport. So that's our Romeo Uniform Quebec at Salisbury. Our next point is going to be the top of our climb. And do a little O because TOC, or Tango Oscar Charlie, is actually an airport. It's near Greenville. It's called Toccoa. So if you put TOC in there, you might think we're talking about Toccoa, which is actually near to the area where I fly out of. So if you do a little O, it's a little bit easier to remember. And then our cruising altitude is going to be 8,500 feet. And then we put our checkpoints. So it could be something like a lake, a tower, a town. I remember we were going to pass over that town. So you could put anything you like, just things that you're going to use to check your course. Make sure that you haven't drifted too far left or right. Notice that the way this is set up, we have, well, let's flip this over and just talk about this. If this is point A, and this is point B, and this is point C, you draw a line between the points. It's not the straightest line, I'm sorry. 2 points are required to make a line. So this right here is a leg. So we have point A and point B, and then between them is a leg. We have point B and point C. Between them is another leg. That's how this navigation log is set up. We have 2 points, and between those 2 points is the line that's drawn between them. That's why it looks like these two kind of come together to make this one, and these two come together to make this one. These are the legs, these things, and these over here are the points. So here's A, B, C, if that makes any sense at all. So we know that our course as we take off out of Salisbury is 311 degrees. That's going to stay the same for both of those for now. Now our altitude between Salisbury and the top of our climb is changing. So we're going to put an up arrow. We are in the act of climbing during this leg. Our wind between the surface and 8,000 feet, well, on this particular day, we know that the TAF for the time we take off is going to be 050 at 4 knots. We're going up to 8,500 feet where the wind is basically calm. 8,500 is slightly less than 9,000, but it's pretty close to 9,000, so we can use that wind calm. So by the time we get up there to 8,500 feet, we know the wind direction is just going to be negligible, velocity negligible, so I'm just going to cross it out. Temperature is 12 degrees Celsius. But while we're climbing, we need the wind that's going to be affecting us during that climb. So if it starts off at this, and then as we get higher up, so if it starts out at 050 at 4 knots, and then the wind eventually becomes 0, on average throughout our climb, we could expect winds. Well, if there's no direction for this, the direction is still going to be 050. The velocity is going to be less than 4 knots because the wind is dying off as we climb higher. So this brings up another interesting point. An airplane does not climb linearly. When we take off, so if here's our runway, I'm not the best at drawing these little things. When we first come off that runway, I mean, we've got a pretty good climb rate. This thing is climbing fast. So if this is our altitude over here, the higher we are on this, the higher our altitude. And this is our, and there's an E on that. And this is our distance or time. Doesn't really matter for my purposes here. As we get higher, though, the plane's not going to climb quite as fast. The air gets thinner, the engine makes less power. We need to start leaning the mixture some. Our wings aren't making as much lift. It starts to taper off, and there will come an altitude where our plane can't climb anymore. It just kind of levels off almost, even though we're at full throttle and holding VY, best rate of climb speed. It'll just level off. That is our absolute ceiling. For most naturally aspirated airplanes, it's, at least in the area where I fly, this is around 15,000 feet. Not a good idea to go that high, though. The engine and magnetos are not calibrated for it. But see this, we started out at this really good climb rate. We're climbing, if we took a point here, we're climbing like this. But here we're climbing more like this. Do you see how the slope of this line changes? We're actually getting into some very basic calculus concepts, but don't worry about that. But if you have taken calculus, this should seem a little bit familiar. If not, no problem whatsoever. I have no qualifications to teach it. I just remember this basic concept of it. So as we climb, the slope of this line starts to get less. See that? As we go along the curve. So what we need to be aware of is we're going to spend less time at these lower altitudes than these higher altitudes. If we split this straight down the middle, let's say we're climbing up to 8,000 feet before we level off. So if this is 8,000 feet here, then we're going to go straight across, or our 8,500 feet, sorry. There we go, 8,500 feet. So we took off out of Salisbury. We're climbing at 8,500 feet, or to 8,500 feet. We can't just assume the wind is going to be right here at the midway point between those altitudes. Because if we actually measure this and look at it, our halfway point is about here. But notice that we're spending more time in this second section. Because the plane's climb rate slows down as it gets higher, we spend more time at these higher altitudes. So our average wind, or the wind that would really be affecting us, is not going to be halfway between our calm and this. It's going to be a little bit closer to the higher altitude winds because we spend more time at those higher altitudes, because the plane slows down as it climbs. I hope that makes sense. I've tried to explain it a few different ways, but just think about it. Because we climb fast, we spend only a little bit of time at the low altitudes, and we spend more time at the higher altitudes. So our wind estimate for this leg needs to be not quite halfway, a little more than halfway. So halfway exactly between 050 at 4 and nothing is 050 at 2. But that's not the best estimate for what our wind is going to be like. So I'm going to do 050 at 1 knot. This is more similar to the higher level winds because we're spending more time at those higher levels. And our temperature, 12 degrees Celsius up there, and at the surface, right now it's 25. There's not really a forecast for temperature in aviation, but you could pull out your normal weather app and look at what the temperature forecast is for the day. I think that's fine to use, at least for a temperature calculation. But let's just say we're going with that 25 degrees Celsius. Halfway between 25 and 12 is going to be 21 and a half. I did that backwards, didn't I? This brings up another point. Use pencil. The only reason I'm using pen on this nav log is because it shows up better on the camera. So yes, please use pencil so you can erase things and not have to do that. Halfway between 25 and 12 is 18 and a half, but we're going to be closer to these lower temperatures. So let's call it 17 degrees. And I'm going to have to write it small because I confused myself and wrote the wrong one. There we go, 17 degrees. Not quite the halfway point, but it works because, again, we're spending more time at those higher altitudes while we climb. Okay, so now we have that stuff in check. What are we trying to calculate? Our goals while calculating climb performance is to figure out the time, that one, distance, and fuel to climb. These are the three questions we're trying to answer while calculating our climb performance. How much time is it going to take? How much distance is it going to take? And how much fuel are we going to spend getting from our starting altitude to our ending altitude? So let's get into this. The field elevation at Salisbury is 772 feet above sea level, if I remember correctly. And we're climbing up to that 8,500 feet. If you're lucky, you're flying a Piper Cherokee of the later models, like a Piper Archer. A Piper Archer has this fantastic chart in the POH, in the Pilot's Operating Handbook, that is exactly what we need. See this? Time, distance, fuel to climb. Time, distance, fuel. So this is the best situation. You're flying a plane that has a chart like this that gives you all three of those things all on one chart. So good on you, Piper, for making a chart that's actually helpful and doesn't require calculus understanding to make it work. To use a chart like this, start over on the bottom left and work your way over. So outside air temperature. Well, what outside air temperature are we using for 8,500 feet? Outside air temperature is 12 degrees Celsius. So here's the Fahrenheit scale up top. You can see the right here. Here's Fahrenheit. Here's Celsius. So 12 is right about there. So when you make your mark on 12, take yourself a nice straight edge. These triangles are great. Draw a nice straight line that goes up like that. There's our 12 degrees Celsius line. Now we need our pressure altitude. Pressure altitude is a little bit tricky to calculate, but basically what we want is our pressure altitude at 8,500 feet. How are we going to do that? Well, we need to know the pressure in the area. Let's look at the METAR because there's not really a good forecast for pressure. So if we look at the METAR, which is the conditions now at Salisbury, we can see altimeter 3002. If you remember, standard altimeter setting is 2992. And we have 30.02. This is actual. The difference between these is a very important number for us. So 3002 minus 2992, just subtract the bigger one from the smaller one. That's going to give us 0.10. See, the difference here is 0.10. If you recall, standard pressure loss with altitude, for every 1,000 feet we climb, we're going to have a decrease of 1 inch of mercury per 1,000 feet. So if 1 is equal to 1,000, 0.1 is going to be equal to 100. See that? So we have 100 feet difference. And if you needed to know, 0.01 is equal to 10 feet. We're just moving decimal points here. So this 0.10 inches of mercury difference from standard is going to be equivalent to 100 feet. So our airport elevation is 772 feet, and we'll get to calculate it up at 8,500 feet. We'll get to there. We have 100 feet difference. So 100 feet. It's going to equal, well, are we adding or subtracting here? Pressure is higher than standard, so I guess we should add, right? No, definitely don't add, because if pressure is higher than standard, the air is going to be acting like it's lower than actual. Remember, pressure gets higher as we go lower, so we're subtracting. Our pressure altitude is 672 feet at Salisbury, not 872 feet. If pressure is higher than standard, our airplane is going to act like it is lower than actual because we have more air pressure than we're typically used to getting. So there's our pressure altitude, 672 feet. All the way up at 8,500 feet, we can use the same conversion. It's not going to be perfect, but it'll be close. So if we subtract our 100, we're going to have a pressure altitude of 8,400 feet if we were at 8,500 feet above Salisbury. So now we have our pressure altitudes. Let's keep calculating it out for our cruising altitude. So our pressure altitude is 8,400 feet. I guess I didn't draw my line far enough. That's not good. Fortunately, it's an easy fix. All I have to do is line this thing up again and continue my line. There we go. So if our pressure altitude is 8,400, there's 10,000 feet, there's 9,000, there's 8,000. So we could imagine a line halfway between these. There's our 8,500 feet, right there on that. But we're a little bit lower than that, so we'll bring that down just a hair. And that puts us right about there. See that? We're a little less than halfway between 8,000 and 900. Or sorry, 8,000 and 9,000. There we go. Also notice, mixture lean 100 degrees, rich of peak exhaust gas temperature once we get above that line. So very important that we're leaning the mixture as we climb. below this line. It's mixture full rich, but anyways, don't forget to lean that mixture as we climb. I didn't draw my line perfectly straight. Sorry about that. We'll use that lower line. That's a little bit better. The fuel that we're going to need, well, if you look at that right there, oh, I'm so sorry. I'm throwing all my papers around while I'm trying to grab my thing. There it is. So if we follow the fuel line, fuel gallons, take that straight down, it's going to take us, look at that, 5 gallons of fuel. Chart includes fuel allowance for start, taxi, and takeoff. So that's part of that. So we can expect 5 gallons, right? No. We'll come back to this. But 5 gallons of fuel. Our time, look at that, 22.5 minutes. So we can expect 22.5 minutes to climb. And our nautical miles. Don't use statute miles because we typically use nautical miles these days. We line that up. Follow that line straight down. It's going to take us 31, yeah, let's call that 31 miles to climb. By the way, the farthest distance you want between checkpoints is typically 15 miles, so we may need a point in between the top of our climb and Salisbury, just for staying on track. I'm not going to do that for this example, but just know in your own flying, you might have 2 of these points that are 2 of these legs where you're climbing, and then so you have a checkpoint that you fly over, and then you hit the top of your climb when we're climbing all the way up to something like 8,500 feet. That's a pretty long climbing period. As you saw, it takes over 20 minutes. This answers all our questions. Why didn't I write it in here? Well, the reason is, this is assuming we started at sea level and climbed all the way up to that pressure altitude of 8,400 feet at 12 degrees Celsius. This is not factoring in the fact that we're starting at 772 feet above sea level. Where did I write that down? Oh, I wrote it over here. Sorry. This is not accounting that we're starting at 772 feet. Now, we know that our pressure altitude is actually 672 feet. So we need to calculate this for our starting altitude. Here's sea level. Here's 1,000 feet. We're going to be somewhere between these. We know our outside air temperature is 25 degrees Celsius over at Salisbury. Oh, let's switch colors, how about? So as before, we'll line it up, your outside air temperature, and draw a line. Now, we're not quite 500 feet above sea level, we're a little bit higher than that, so let's go right here. There's our 672 feet pressure altitude. Looking at our fuel, there's 2.5 gallons. We're losing about half a gallon right there, so there's 0.5-ish. So if we follow that straight down, it puts us right about here. This would be 2.5 gallons, so we're just going to be safe and call that half a gallon. As far as time is concerned, we're losing, sorry, that's about 3 minutes right there. And just following that down, see, this line here would be 2.5 minutes because we're halfway between 0 and 5. Where that intersects, we're a little bit to the right of that, so that puts us at about 3 minutes-ish. This is not going to be perfect, but it's going to be close. Nautical miles, we're looking at roughly, again, 3 nautical miles. So this here, this half gallon, this 3 minutes of fuel, or sorry, this 3 minutes and this 3 nautical miles. Half a gallon fuel, 3 minutes, 3 nautical miles. We need to subtract these from these to get our accurate numbers, because we did not start at sea level. We started at 772 feet. 5 gallons minus half a gallon. That's going to be 4.5 gallons of fuel. Our time is going to be 22.5 minus 3. So that's going to be 19.5. 19.5 is our estimated time en route, ETE. And then 31 nautical miles minus our 3, that's going to be 28 nautical miles. And there we go. Look at that. We've calculated our time, distance, and fuel to climb from Salisbury up to 8,500 feet, factoring in the pressure and temperature of the day. So that's pretty good. If you're flying a Piper, you get to stop there, which is fantastic. Sadly, though, it's not that simple. For most of us, at least. Most planes have a chart that looks like this one. Climb performance, you have some numbers, and all it gives you is a rate of climb in feet per minute. That's annoying. That's very annoying. Because a rate of climb in feet per minute, if you remember, if I come back over here, these are rates. So if we calculated our climb performance at takeoff, it would give us a line that looks something like this. And then that would say that it would only take this much distance and fuel to climb, but in actuality, it's going to take this much. So that's a huge problem because our climb rate at takeoff is not the same as our climb rate when we're here. Okay. What if we used our climb rate halfway? That's going to work really well, right? So let's do our climb rate halfway. Use that feet per minute and fuel. Well, that's still going to underestimate how much time, distance, and fuel it takes to climb. Remember, we're slowing down as we get higher, so that doesn't work either. What we need is somewhere that's halfway with a little bit of bias. One number that I heard was 60 or 70%. Let's go with that 60% figure. So if we used a point 60% of the way, that would put us about here. And if we use our climb rate there, as you can see, that's going to put us much, much closer to our actual. Because as we climb, that climb performance gets lower. And I'll draw our real climb performance in blue so you can see that again. I've drawn too many lines on top of it. I'm sorry about that. There's our real path. A chart like this only gives us one climb rate in feet per minute. We're trying to approximate a curved line with a straight line. That's the problem. That's the problem that we're running into here, is that these charts only give us a straight line, but we really need a curved line to be the most accurate. So if you use this 60% rule, that's going to get you close. It's not a perfect estimate, but it's close. So 60% of what? Well, we're starting at 772 feet. And we're going to do this in pressure altitude. So let's do our 672 feet. And we're going up to 8,400 feet on our pressure altitude. Let's subtract those. For those who don't know, your electronic E6B also has a calculator built in, just like any normal one. So you can do your 8,400 minus 672. And don't hit enter, hit equals. There we go. That's how much we're climbing. 7,728 feet. 60% of this is, well, to get that, you would multiply times 0.6. That's how you do 60%. So let's take that number times 0.6 equals 4,636.8. So we want a feet per minute at about 60% of the way from our takeoff to the ending of our climb, and that's going to put us really, really close. If you didn't notice, I just made a huge mistake. I forgot to add that 4,636.8 feet to our starting altitude of 672 feet. That gives us roughly 5,300 feet. That is the pressure altitude I should have been using here. It's not a huge difference, but it is a major mistake, and please don't make the same mistake that I did. Make sure you add that 60% figure back to your starting altitude so you truly are calculating a climb performance for 60%. And if you're climbing to something like 12,000 feet, you might want to use something more like 70%. But for this example, let's just stick to 60. Our temperature at 60%, well, we can do the same thing we just did. We know it's 12 degrees up at altitude, and it's 25 here at the surface. So 25 minus 12. There's the difference between them. Multiply that by your 0.6. Add that to your starting temperature, or subtract that from your starting temperature. 25 minus 7.8. Basically 17 degrees again. Oh, look at that. It's the same temperature we calculated by picking our halfway point and going just a little bit extra. So just a basic estimate that was a purely educated guess got us very close to the actual figure that we wanted. All right, now we have our pressure altitude and our temperature at that pressure altitude, approximately. Let's calculate it out. Our outside air temperature, we just figured out was 17 degrees. Let's put a mark right there at 17. It's right about there. And then let's draw our line straight up. And then we need our 4,636 feet. Here's 4,500. We're going to go just a little bit more. Hey, look, it just so happens to be right on that line. That's fantastic. We'll follow that straight across, and we get a climb rate right there of, there would be 500 feet per minute, 450 feet per minute. We have a climb rate. That doesn't tell us anything, does it? Sadly, no. We still need a way to calculate our time, distance, and fuel to climb. So how do we get our time, distance, and fuel to climb from a simple number like 450 feet per minute? We have feet per minute, and we have feet. All we need is minutes. If we're climbing 450 feet every minute, and we need to climb 7,728 feet, what if we just divided those? That would give us our time. 7,728 feet of altitude that we are trying to climb, divided by our 450 feet per minute. That gives us 17.17 minutes. That's a little less than we estimated with the more accurate chart, but remember, this is a less accurate method, but sadly it's the only one that we have. So our time, at least with a lot of airplanes, it's the only one that you have. So 17.3-ish minutes. So we're able to get our time just by dividing our altitude change by our feet per minute estimate. So that's our time to climb. All right, how about fuel? You're going to have to know your airplane. A lot of airplanes are going to have a fuel flow gauge. If you are lucky enough to have a fuel flow gauge, look at it next time you're climbing. If you don't have one, you could use your cruise performance. I know that typically a Piper Cherokee burns about 9 gallons per hour. At cruise, we're doing about 75% power. So going up to 100%, it's logical that we're going to be burning about 12 gallons per hour in climb. Please don't ask how I did that math. If you want to be more conservative, you can add even more. This is just what I know from these airplanes that I'm flying. It's probably going to be different for yours, so just please be careful there. But come up with a reasonable estimate for how much fuel per hour you're burning. We have our time, we have our gallons per hour. Well, 12 gallons per hour, there's 60 minutes in an hour, that's going to be the same as 0.2 gallons per minute. For climbing for 17.3 minutes, multiply that by 17.3. So that's the same as 0.2 gallons a minute. That, you multiply those two, gallons per minute times minutes, it's going to give us gallons. It's 3.46 gallons of fuel. One thing I forgot that I just realized. When we calculated our time, distance, and fuel to climb here, I used that 12 gallons per hour. That does not account for taxi and startup. For a Piper Cherokee, go ahead and add about 1.5 gallons. So that plus 1.5 is going to equal about 5 gallons of fuel when we do our start, taxi, and run up. That's going to be a much more accurate estimate. 1 gallon is also pretty good, but I tend to take my time, so 1.5 gallons is going to be a little bit better. The last one is distance. We're climbing at 76 knots indicated airspeed. On a hot day, the plane's going to be going a little bit faster than that. You can calculate out your true airspeed, so let's do that. Speed. Actual true airspeed. Pressure altitude. Hey, look at that, we already calculated it. At 60% of our climb, our pressure altitude is 4,636.8. Our temperature outside, 17 is what we came up with, 17 degrees Celsius. Calibrated airspeed. Well, I only have indicated. If I went into the POH, I could find a conversion. I just know from memory that the Piper is very accurate around that 76, so we'll put 76 straight in. But refer to your POH and convert indicated to calibrated. Gives us a true airspeed of 83 knots. So even though our airspeed indicator says we're going 76 knots through the air, we're actually doing 83. And the reason is the air is thinner, so it's not going to create enough pressure on your pedostatic system and the instruments to make it look like the true 83 that it is. That said, your plane will always stall at the same indicated airspeed at 1G. So even though true airspeed starts to go higher than your indicated airspeed, keep using your same indicated airspeeds that you're used to. That's very important for safety, especially when you're at a higher altitude airport. Don't be rotating or trying to climb at your true airspeed. Do it indicated. You need extra speed when it's a higher density altitude, when you're at a higher altitude airport. So keep maintaining that 76 like you're supposed to. If we're going 83 nautical miles every hour, we could divide that by 60 and get nautical miles per minute. So that's what we need to do. To get out of this function, just turn the calculator off and back on, then it goes back to being a normal calculator. 83 divided by 60, because there's 60 minutes in an hour, 1.3833 nautical miles a minute. Hey, look at that, we already have minutes. So that number times 17.3, our minutes, roughly 24 nautical miles. Just from a very standard, very boring chart that gives us a climb rate, we can calculate out our time, distance, and fuel to climb, just like we did with the more detailed chart. It took a lot of extra work to get there, but you can still do it. Those are 2 ways to calculate time, distance, and fuel to climb. I'm going to give you another example. And this is the chart that comes from the Cessna 172. I despise this chart. Cessna did not do a good job here. It only gives us 4 different points and then a few other notes that we can use. So to use this Cessna chart, just as before, we need a climb rate that's not quite halfway, a little bit extra, so a little past halfway throughout our climb. A chart like this one over here is much, much better because it can give us a wide range of climb rates. The Cessna chart is not so detailed. We just have to be more careful with it. The nice thing is, though, it does give us different weights. So weight will affect your climb performance, and that is one thing the Piper charts do not account for. They assume maximum gross. So you have no choice but to use maximum gross. When we're doing a training flight, we're usually pretty close to 2,000 pounds in the Cessna 172s that I fly, so we'll go with that. Again, indicated airspeeds, they've got them slowing down for some reason, probably because you might get a slightly better climb rate. I don't recommend that. I would recommend maintaining the same VY, but that's what they say here for the maximum climb rate. I'm just going to skip past that. So, sea level at 59 degrees Fahrenheit, 5,000 feet. What's closer, sea level or 5,000 feet? Well, we need that altitude that's 60%, 4,600. That's really close to 5,000. In this case, I'm just going to use the numbers straight off of 5,000. But if we were climbing to a lower altitude, we could use a number that's halfway between these two. There is a fantastic video on calculating takeoff performance using the Cessna charts by Free Pilot Training. I will link that in the description. But one of the things that he said was, if you're in doubt, go ahead and use the worst one, the higher one, because then you're going to have a margin of error. You're going to have a safety margin. This is all a great idea to have. So use halfway. If you're more than halfway, go ahead and round up to the higher one. We're easily more than halfway, so let's just use 5,000 feet data. Rate of climb, look at that, 610 feet per minute using 2.2 gallons of fuel. Now, we're not starting from sea level. We're starting at 772 feet, but we don't really have a good way to factor that in, so let's just go ahead and keep with that 2.2 gallons for the Cessna. Now, if we were starting off at like a 2,500 foot airport, we could look at the difference between these. So there's 1 gallon, there's 2.2. Halfway between those is 1.6. So we could subtract some of that. Now we need our time. So it gave us a feet per minute of 610. But flaps up, full throttle, mixed or lean for smooth operation above 3,000 feet. That's a much better figure than what the Piper's saying. I try to lean the mixture anytime our density altitude is more than 3,000 feet. This doesn't say density altitude, but I do recommend that. Fuel used includes warm-up and takeoff allowance, and that's good to know. For hot weather, decrease rate of climb by 20 feet per minute for each 10 degrees Fahrenheit above standard. Well, 41 Fahrenheit at 4,000 feet, I don't know what that is in Celsius. Good thing our calculator can do it for us. 41, convert Fahrenheit to Celsius, 5. Well, 5,000 feet, we calculated out it's going to be about 17 degrees. So, what's 17 degrees? Now we're going to convert Celsius to Fahrenheit. That's 62.6. So 62.6 minus our 41. This calculator is really helpful. It's going to equal 21.6. So decrease 20 feet per minute for each 10 degrees Fahrenheit above standard. That's going to be a good 40, let's call it 45 feet per minute. I'd added a little bit extra because we're a little past 20. Let's call that 45 feet per minute more. So we have 610 minus 45. That's going to equal 565 feet per minute on our climb rate. As before, we know that we're climbing that 7,728 feet. So 7,728 feet of climb. And remember, I got that from our starting altitude and our ending altitude, the difference between them. We're starting at 772 feet above sea level. We're ending at 8,500 feet above sea level. I used pressure altitudes, but it's fine. We only subtracted 100 from both of those. All right, that's our distance that we're climbing. Divide that by our feet per minute, and that's going to equal our time to climb. So 7,728 divided by 565 equals 13.67, let's call it 68 minutes. So we have our fuel, we have our minutes. The last thing we're going to need is our distance. Well, we have our indicated airspeed in miles per hour, 80. We need to convert that to knots. Yes, this calculator is capable of doing that. We need to convert miles per hour to nautical miles per hour, or statute miles to nautical miles. So convert statute miles to nautical miles. There we go. We're climbing at about 70 knots. So 70, or that number, divided by 60, because remember there's 60 minutes in an hour, we're covering 1.15 nautical miles every minute. We're climbing for 13.68 minutes, so that times our 13.68. Notice that it didn't record the decimal there. Sometimes your calculator won't quite notice everything. So before you hit enter, make sure you double check that you typed it in right. I just messed it up again. There we go. 13.68, enter. That's going to be roughly 16 nautical miles, NM, not MN, to climb. So now we've calculated time, distance, and fuel to climb using 3 different methods. One of a really good Piper chart, one of a more standard, not great chart, and one of an even less standard, even less great chart. So if you notice, the common theme between these is that we're finding a value that's not halfway between our starting altitude and our ending altitude. It's a little more. It's a little higher because the plane slows down as it climbs. With that foot per minute climb rate estimate, we're going to divide our total altitude change. So our ending altitude minus our beginning altitude. We're going to divide that, and that's going to give us minutes to climb. With minutes to climb and a fuel burn rate that we know of, we can calculate gallons. And with that, we can then move on and calculate distance just by converting how fast the plane is going, 60 to get nautical miles per minute, and then we just multiply that by our minutes to get how many nautical miles we've covered in that many minutes. That's how you get time, distance, and fuel to climb. And if you want to stop there, I think that's okay. But if you do want to be really detailed and factor in wind, let's figure out how to do that. So for our last example, we could use any of these. I'm just going to stick with this Cessna demonstration that we just did. Let's calculate how wind would affect us. Would wind impact the time it takes to climb? It's going to have 0 impact on our feet per minute. So it's not going to change how quickly we get from our beginning to our ending altitude. Whether the wind's blowing us this way or this way, it doesn't change the time. I'll have to cross out the distance there, but it's not going to change the time that it takes to get up there. So this number right here is still good, even if there's wind that we're fighting. Fuel. We calculated fuel based on time, so that's not going to be affected either. So you calculate your time and your fuel the exact same way, whether or not you're factoring in wind. Okay, great. The only thing that changes with wind is going to be your distance that you fly while you're climbing. If there were a headwind, the wind blowing this way, as the plane climbs, it's going to be pushed backwards. So we're going to cover less distance over the ground. If you have a tailwind, it's going to push you forward as you climb, so you're going to cover more distance. Hey, this sounds almost like calculating our cruise performance, because it is. Do your heading ground speed. Put in your wind direction. I'm going to use the winds from 12,000 feet just because it's a wind value that we already got. So 310. That's a headwind for our route of flight. Wind speed, 9 knots. Our course is 311. Our true airspeed, I'm going to stick with 70 for now, just as an estimate in the interest of time, but yes, you could calculate out your true airspeed the same way we did before. And now we have our ground speed, our heading, and our wind correction angle. Hey, we needed those anyways for filling in these next few parts of our navigation log. That's a lesson for another time. There are also other people who have made videos on that, and maybe you should do that with your instructor as well. But this climb performance is what we're focusing on today, so we're going to hold off on that. The real number I care about here is ground speed, 61. Our 70 went to 61 because that wind is slowing us down. So instead of doing 70 divided by 60, we're going to do 61 divided by 60, our ground speed. So let's turn the calculator off and back on just to get it back to normal calculator mode. 61 divided by 60, we're going to be covering almost exactly 1 nautical mile per minute. And if we're climbing for 13.68 minutes, 13.68, that's going to be 14 minutes. 14 nautical miles. So our 16 nautical miles now becomes 14 when we factor in that wind. And that makes complete sense. Because the wind was slowing us down, we're going to cover less distance as we climb. It's really the same. When you're climbing, you still use your heading and ground speed calculation. Just factor in the wind. And when you're dividing your airspeed and multiplying it by your minutes, just divide your ground speed rather than your airspeed. And that will factor in the effects of wind. Other than that, it's not going to have a whole lot of impact on your climb performance. It's only going to impact the distance that you've covered. So there you go, 4 different methods for calculating time, distance, and fuel to climb for 4 different situations. Hopefully these methods can give you a general idea of how to move on with your own climb calculations on the aircraft that you were flying. And if you have any questions, feel free to post them in the comments or rewatch the sections that you need to. Again, please remember, this is not a replacement for your instructor. This is not a replacement for sound judgment and common sense. When you're planning out your climb, add safety margins, add a little extra fuel. And the last thing I want to leave you with, remember, when you're doing any kind of calculation for performance on your aircraft, if one of the numbers you got does not make sense, go and double check. If it doesn't look right, it probably isn't. So play it safe, add safety margins, be very careful. You are the pilot in command of an aircraft, so treat that accordingly. I hope you enjoyed. Thanks for watching, and I hope you have a nice day.